Hi, welcome back to the channel. In today's lesson, we'll take a work example in specific heat capacity. It will help us understand the concept of specific heat capacity and how to solve problems relating to specific heat capacity better. In case you missed our last lesson where we explained specific heat capacity, please do not hesitate to check the description below. That said, let's get into class. Our question says, a water bath contains 15 kg of water at 50 degrees Celsius. If cold water and hot water taps are turned on such that they deliver water at the rate of 30 kg per minute. Now, let's take it this way. Here's a jar. This jar contains 15 kg of water. This is 15 kg of water. Now, I have hot water turned in. Here's hot water. And I have cold water turned in. Here's cold water. Cold water. Cold. Now, this tap runs for 20 minutes. And if the temperature of the hot water is at 100 degrees Celsius, the temperature of this hot water here is at 100 degrees Celsius, and the temperature of the cold water is at 15 degrees Celsius. Remember that the temperature of the water in the jar itself is at 50 degrees Celsius. Now, with this, we are asked to determine the temperature of the mixture, the temperature of the total mixture after 20 minutes. Now, let's remember that this water runs for 30 kg per minute. So, in 20 minutes, both taps would have delivered 30 kg, would have delivered times 30. That is, they would have delivered 600 kg of water, making 1000 for times 2. Times 2 of this, let's multiply it by 2. Times 2 of this, they would have delivered 1200 kg of water. Now, since there's going to be an heat loss and there's going to be an heat gain, there's going to be an heat loss from the hot water and there's going to be an heat gain from both the cold water and the 15 kg of water in the tap. So I'll be taking it this way. Remember that we say quantity of heat dissipated from our last lesson is equals to mc delta theta, where the quantity of heat, the change in heat is, or the quantity of heat gain or change in heat is the Q, my M is a mass, my C is the specific heat capacity, and delta theta is the change in temperature. In case you missed our last lesson, please do not hesitate to check the description below, and also please do not hesitate to hit the subscription button. That way you'll be sure to get notified anytime we create lessons like this. Now from our diagram, we said the quantity of heat gained by both the water in the jar and the cold water will be equal to the quantity of heat loss by the hot water. So we'll be saying that quantity of heat gain, I know that heat gain is equals to heat loss. So that we'll be saying that heat gain is the heat from the hot water. The hot water is going to run from 30 kg of water that's running for 20 minutes. That's 30 times 20 times, remember we're talking of Q is equals to mc delta theta. So that my M here is 20 times 30. Then my C, specific capacity of water, we've been given specific capacity of water to be 4.2. That's 4.2 times a change in temperature, that will be 100 minus this heat, the temperature we are looking for. That is the final temperature of the mixture. Now this is equals to, now heat loss will be both by the 15 kg of water times specific capacity 4.2 times, now let's assume temperature was raised, or let's assume it even have a lower temperature below 50, which we are not sure. Let's say 50 minus theta. Now plus the heat gained by the hot water, by the cold water, that will be 30 again times 20, because we have 30 kg of water running for 20 minutes times 4.2 times, but now we are having an heat gain because the temperature is going to increase. That will be because times theta minus 15 degrees. times theta minus 15 degrees. Now, so that I have 600 times 4.2. So that for my heat loss, I have 600 times 4.2 times, okay, that's 600 times 4.2, that's 2520 into 100 minus theta equals 15 times 4.2, 15 times 4.2, that's equals to 63, equals 63 into 50 minus theta plus 20 times 30 again, that's 600 times 4.2, that should be 25 again, 2520 into theta this time minus 15. So that should have 2,52000, that's 2,520 times 100 minus 2,520 times theta is equals to 63 times 50, that's 63 times 50, that's 3,150 minus 63 theta plus 2,520 theta minus 2,520 times 15 minus 37,800. Now, so that I should have, now let's collect like terms. Let's push all the thetas to this side and bring all other figures to the other side. Then I should have 252000 minus 3150 plus 37,800 equals 2520 theta plus this other 2520 theta goes to the other side also to become positive 2520 theta minus 63 theta. In case you want to understand how to change subject of formula, I will include one of our lessons on change of subject formula in this example. I believe it will help you understand how to make subject of the formula. Now this, if you sum up 2,000, 25,000 or 252,000 together minus 3,150 plus 37,800, that should sum up to 286,650. Now this is equals to, now if you sum up the left hand side, 2,520 plus 2,520 minus 63, we should come up with 4,977 theta from my calculator. Now let's divide both sides by 4,977 theta, and let's divide this side also by 4,977, so that theta will be equals to 2,000. By the time you divide that, you should come up with 57.594 degrees Celsius, which is approximately 58 degrees Celsius. Now, that means the final temperature of the mixture should come to 58 degrees Celsius, assuming heat is not totally lost. Heat loss is equals to heat gain. With that, I hope you understand how to treat questions relating to specific heat capacity. In our next lesson, we'll still come up with other questions that will help you understand it better. Thank you for staying with us, and do see you in our next class. But to ensure you get our next lesson, please do not hesitate to hit the subscribe button. That way you'll be sure to receive our lessons anytime we create them. Thank you, and see you in the next class.